So, hello friends, welcome to a lecture series on nonlinear programming. Now, the next topic is dynamic programming. So, what dynamic programming is and how it is useful to solve some nonlinear optimization problem, let us see in this topic. So, what dynamic programming problem first, let us see. So, dynamic programming was invented by an American mathematician Richard Bellman in the 1950s to solve some optimization problems. It is used to solve a wide variety of discrete optimization problems such as scheduling, string editing, packaging and inventory management. So, there are many more applications of dynamic programming which is used to solve some discrete nonlinear optimization problems. What is the main concept of this approach of these problems? The main concept is break problems into sub problems which we are called as stages and combine their solution to get the solution of the larger problems. Basically what we have, suppose we have a larger problem, larger optimization problem. So, we divide that larger problem into sub problems and solve the last sub problem, use the data of that sub problem into the next step, and similarly when we solve that problem, that sub problem, we use the optimal solution or the solution obtained from that stage to the next stage. In this way we can solve a larger problem. Okay. Now, dynamic programming is a general algorithm design technique for solving problems defined by or formulated as recurrences with overlapping subinstances. So, what does it mean? We will discuss it by an example. Now, what is the main idea? Main idea is set up a recurrence relation relating a solution to a larger instance to solution of some smaller instances. Okay. Solve smaller instances. Smaller instances means sub problems. You break the problem into sub problems, solve smaller problems, record the solutions, record the solution of that sub problem or that small problem, and then extract solution and use it for the next table. Okay. You take the solution of that small problem or that sub problem and use the solution of that problem into the next table. In this way we will get back to the solution of the larger problems. Okay. Now, how does it come? It comes from Bellman principle of optimality. What does it states? It states that the optimal policy must be one such that regardless of how a particular state is reached, all later decisions or choices proceeding from that stage must be optimal. So, that is Bellman's principle. What does it state? It states that whatever the solution we obtain from the sub problems and use it in the next table, then if we repeat the same process until we get back to the final table, then the solution remains optimal. Okay. So, let us discuss dynamic programming first by a shortest path problem. Okay. Let us discuss shortest path problem first, and from this we will have an idea what dynamic programming problems are and how it is useful to solve some nonlinear problems. Now, first is to find the shortest path in a multi-stage graphs. You see here in this example number 1 we have stages, we have 4 nodes S, A, B, T. These are the nodes or the cities or the stations. Now, these arc indicates the distance from this stage or this stage. It may be a distance, it may be a cost, or it may be some other value. Okay. Say from S to A there are 3 different paths or 3 different costs. It may be these are 3, 1 and 5. From A to B again we are having 3 different paths 2, 4 and 6. Okay. From B to T we are having 2 different paths 7 units and 5 units. Now, what is the problem? Problem is to find the shortest path from S to T. Which path we should adopt so that the distance from S to T is minimum. How to find that path? So, the easiest method is greedy method. What greedy method is? You see, if you start from S and to come to point A or node A. So, from S to A there are 3 paths of 3 units, 1 unit and 5 unit. What is our main aim? Our main aim is to find out the minimum distance or the minimum path. From S to A, out of these 3 paths, which one is minimum? Minimum is this one from S to A, the straight path. Okay. So, let us choose it 1. Then from A to B we have 3 different paths, 2, 4 and 6 units. Out of these 3, which one is minimum? This 2 is minimum, okay, from A to B, this one. So, from S to B, which is minimum? This straight path of 1 unit, and from this path of 2 units, that is total is 3 units. And from B to T, we are having only 2 paths, out of which 5 is minimum. Okay, so this path is minimum. That means if a person want to travel from node S to node T, the minimum distance will be S to A, which is 1 unit, A to B, which is 2 units, B to T, which is 5 units. Total is 1 plus 2 plus 5, that is 8 units. So, 8 units the minimum path or the shortest path from S to T. So, this is greedy method. What greedy method does? Greedy method takes minimum path from one node to another. Okay. So, in this way we cover all the nodes and find out the minimum path or the minimum distance. However, this method is not applicable for all type of networks. You see, if you take example number 2, say you have this network from S to T, we have to find out the minimum path again from S to T. Okay. If we apply greedy method, then from S to S we are having 3 different nodes here, A, B and C. Okay. Which one is minimum? Which one is giving the minimum distance or the minimum path? This one, S to A. If we apply greedy method, okay. Now we come to node A. From A to this stage, we are having A to D or A to E, only 2 paths. Which one is minimum? A to D is 4 units, A to E is 11 units, minimum is 4 units. Okay. That means from S to D it is 1 plus 4, that is 5 units. Now from D to T we are having only one path, that is 18 units. So, total will be 18 plus 4 plus 1, that is 23 by the greedy method. However, this is not the shortest path. If you see this path S, C, F, T, S to C 5 units, C to F 2 units and F to T 2 units, that is 5 plus 2 plus 2, that is 9 units. This is minimum. This is much lower than 23. So, that means greedy method fails here. That means greedy method may be applicable for some simple networks, but may not be applicable for complicated networks. So, how can we find out the shortest distance if we have a complicated network, if we have this type of problem? How to find out the minimum distance or the shortest distance from node A to node P or from node X to node Y? Okay. So, suppose we have this path, we have to find out the minimum path from node 1 to node 10 in the following network. Okay. Here is node 1, this is node 1 and this is node 10. We have to find out the minimum distance or the minimum path from this node to this node. So, how can we proceed for this problem? So, let us see. Here in this network we have to find out the minimum distance from node 1 to node 10. And the path is given to you, say from 1 to 2, node 1 to node 2, the path is 5 units. Node 1 to node 3, the distance is, path length is 7 units. Similarly, if you see from node 5 to node 7, the path is of 8 units. Okay. Now, how to find out the minimum distance from node 1 to node 10? So, we have 2 methods, either we can use backward recursion or we can use forward recursion. Suppose we use backward recursion. How can we solve? So, first is define certain terms. So, first is dij is the distance of the arc joining the nodes I and j. Suppose you want to find out suppose d26. D26 is the distance from node 2 to node 6, node 2 to node 6, the distance is 2 units. So, this is then this is 2. Suppose D710 or D57, okay, D57 is the distance from the nodes 5 to node 7, it is of 8 units. So, it is 8. So, Dij simply stands for the distance from the node I to node j. Okay. Now, if you come to Fi, Fi is the minimum distance from node I to node 10, okay, from node I to node 10. Suppose you want to find out F10, okay, F10, that means the minimum distance from node 10 to itself, that is 0, of course 0. Suppose you want to find out F9, F9 is the minimum distance from node 9 to node 10 as per definition of Fi. Fi is minimum distance from node I to node 10. If you want to find out F9, that means minimum distance from node 9 to node 10. From node 9 to node 10, there is only one path. So, the distance minimum is 9 only. Okay. F8, suppose you want to find out. So, F8 is what? F8 will be the minimum distance from node 8 to node 10. There is only one path here. So, it is of 7 units. Okay. Now, suppose you want to find out F3. Okay. F3 will be what? F3 will be the minimum path, minimum distance from node 3 to node 10. Now, from 3 to 10 we have to find out the minimum path. Okay. Now, 3 is connected to these two nodes 5 and 6. Okay. So, we can say that it is nothing but it is distance between 3 and 5 plus F5 and distance between 3 and 6 plus F6, and the minimum of these two will be F3. Of course, you see this is 3 5 plus F5, F5 will be minimum distance from 5 to 10, that will give the minimum, that will be a distance from 3 to 5, the minimum of these two, I mean distance between 3 and 5 plus F5, okay, distance between 3 to 6 plus F6, the minimum of these two will give the minimum distance from 3 to 10. Okay. So, in general, how can we define Fi? Fi, how can we define Xi? It is nothing but, or Fi, how can we define it? Fi, it is minimum of Dij plus Fj, okay, minimum over j. That will be the minimum, that will be give the Fi, the minimum distance from node I to node 10. Okay. Now, follow the same thing. What will be F7? Again, F7 will be minimum distance from node 7 to node 10. From node 7 to node 10, there is only one path. So, that will be minimum, that is 8 units. 8. Now, suppose you want to find F6. Okay. What will be F6? F6 will be minimum of, now from 6 to 10 we have first we have these 3 nodes, or 6 is connected to first with these 3 nodes and then with 10. Okay. So, first we find D67 plus F7, then D68 plus F8 plus then D69 plus F9. So, the minimum of these 3 will give F6, which is the minimum distance from node 6 to node 10. That is further equal to minimum of D67 is 6 and F7 is 8, D6 8 is 7 and F8 is 7, D6 9 is 4 and F9 is 9. So, it is 13, it is 14, it is 14. So, minimum is 13. Okay. So, from node 6 to node 10, the minimum path length is 13 units, and how we can travel, how can we get 13 from node 6 to node 10? You see, 13 we are getting over here, that means 6 to 9 and then 9 to 10, that is 4 plus 9 is 13. Okay, because 13, this 13 we are getting from this point, and this is F9, that means 6 is connected to 9 and then 9 to 10. The 6 is connected to 9 and then 9 to 10, that is 4 plus 9 is 13. Okay. But we have to find from node 1 to node 10. Okay. So, in the same way we will move backward, and then we find F5, F5 again will be minimum of, it is D, again it is F57 plus F7, then D58 plus F8, then D59 plus F9. It is equals to minimum of, what is D57? It is 8, F7 is 8, D58 is 7, F8, okay, D57, oh sorry, D58, it is 9, okay, so it is 9, and F8 is 7, it is 7, D59 is of 5 units plus F9 is 9. So, it is 16 and 14. So, minimum is 14. So, minimum distance from node 5 to node 10 is 14 units. Okay. Now, F4, we find F4. F4 will be minimum of, now from 4 to 10, first we have these two nodes, that is 5 and 6. So, you first find D45 plus F5 and D46 plus F6. D45 is distance between node 4 and node 5, that is 2. 2 plus F5, F5 is 14. Then D46 is 3, 3 plus F6 is 13. So, it is 13. So, it is 16, minimum is 16 at both the points. It is also 16, it is also 16. Now, similarly F3, okay. So, F3 will be minimum of this 4 plus F5. So, 4 plus F5 is 14. So, 4 plus 14, and then it is 5 plus F6. So, 5 plus F6 is 13. So, it is 18. Okay. Now, what is F2? F2 will be equal to minimum of, now F2, it is 3 plus F5, first 3 plus F5, F5 is 14. So, 3 plus 14, and then it is 2 plus F6. So, 2 plus F6 is 13. So, it is 13. So, minimum is 15. Minimum is over here. So, that means from node 2 to node 10, the minimum path length is 15 units. Now, finally F1, because F1 is to find out. F1 is a minimum distance from node 1 to node 10. This is to find out. Okay. So, F1 is minimum of, now F1, it is 5, this distance 5 plus F2, 5 plus F2, F2 is 15, and then 7 plus F3, F3 is 18, then 7 plus 18, and then 6 plus F4, 6 plus F4, then 6 plus F4 is 16. So, it is 16. So, minimum of these three is, it is 20, it is 25, it is 22. So, minimum is 20. So, the minimum path length from node 1 to node 10 is 20 units. What is the path of 20 units? Now, how to find that? You see, this is 20 unit, which is a minimum distance, minimum path length from node 1 to node 10. We are getting this 20 over here, this is 20. Okay. Now this 15 we are getting from 2. So this 15 we are getting from here. This is F2. Okay, this is F2, this was F2, this was F3, this was F4. Okay. So this 15 we are getting from here. Now this 15 we are getting from here. Okay. Now this is minimum of this F2. Okay. This F2 minimum of 3 plus F5 and 2 plus F6. So it is F6. It is 2 plus F6. So it is F6. Okay. Now come to F6. F6 is here. This is 13. This 13 is over here. So first we move from 1 to 2. This is F2. Okay. First we move from 1 to 2, and then from 2 to 6, okay, and then from 6. Now 6, this 13 we are getting from here, and this is F9. From 6 we are getting to 9, and from 9 we are getting to 10. There is only one path, so that is this path. Now, so path is 1 to 2, then 2 to 6, then 6 to 9, and then 9 to 10. If you take this path, it is 5, it is 2, 5 plus 2, 7, 7 plus 4, 11, 11 plus 9 is 20. So that is the minimum path length is 20, and the path is 1 to 2, 2 to 6, 6 to 9, 9 to 10. So this is how for such networks we can easily find out the minimum path length from node 1 to node 10. Okay. Now this is backward recursion, because we started from node 10 and come to node 1. Now same lines, on the same lines we can also use forward recursion. We can let Fi as minimum path from node 1 to node I. If we define Fi like this, so instead of following as a backward direction, we will move in the forward direction. Okay. So same thing is given in the PPTs also. You see, there is a path length is 1 to 2, 2 to 6, 6 to 9, 9 to 10, and that we obtain from here F2, then F6, then F9, okay, and F9 is 9. From there we are getting, and this is forward recursion algorithm. Forward recursion algorithm, we define the minimum distance from node 1 to node j like this, and using the same concept we can easily find out the path is 1 to 2, 2 to 6, 6 to 9, 9 to 10. So this is just an illustration that how can we solve such a complicated network using forward or backward recursion. But this is not a dynamic programming approach. So how can we solve this type of problem of shortest path using dynamic programming approach? So that we will see in the next lecture, that how can we solve such problems using dynamic programming approach. So thank you very much.